Well, in the first two videos in this series, we looked at the algebraic side of complex numbers and then the geometric side of complex numbers. In this video, we're going to talk about something called the polar form of a complex number. And a polar form is going to be really nice because it's going to very nicely capture the geometry of what's going on with complex numbers and really simplify the kinds of computations that we might wish to do with complex numbers. So where were we? Last time, we'd seen that complex numbers could be represented as some length r times cos theta plus I sine theta. And this representation of complex numbers was particularly nice because this way of representing complex numbers was really nice because we could understand what was going on geometrically in a very transparent way. The r, the real number that's out the front, represented stretching by r. And what I mean by this is if you take some complex number and then multiply it by this specific z, the effect of that multiplication, well, the r portion of that z is a stretching in the complex plane. And we also saw that the other portion, the cos theta plus the I sine theta, if you multiplied by z, you took whatever you started with and you rotated it by an angle of theta. And as such, complex number multiplication was just some combination of stretches and rotations. That's what multiplying by complex numbers were. Now, I want to show you a very important formula, one of the most important formulas in mathematics called Euler's formula. And what Euler's formula does is clean up this presentation in some sense. That is, the formula says e to the I theta is cos theta plus I sine theta. That is the exact same cos theta plus I sine theta that we saw in this way we represented our z. Euler's formula is particularly nice if you plug in the value theta equal to pi, then you get e to the I pi is minus 1 plus I times 0, just minus 1. And this formula is very aesthetically pleasing because it lets you relate many of the special numbers within mathematics all in one sort of formula that you almost wouldn't possibly believe can be true. Now, in this video, we're not going to prove this statement. Indeed, this video was filmed in the context of a Calculus 2 course where later on in the course, students will be exposed to infinite series, and there's a standard proof of this using infinite series. I do want to note, well, what is this exponential function? I mean, if it was e cubed, you'd say that was e times e, but what do you mean by e to the power of I times theta? So this is defined in what we call a series expansion. The idea is that e to the x is 1 plus x squared over 2 plus x cubed over 6 plus x to the fourth over 4 factorial over 24, and so on and so on and so on. It keeps up that basic pattern. The reason I like this series expansion is I can imagine plugging any number x into that series expansion now, I theta, for example, whatever that number turns out to be, I could just plug that in and square it or cube it or take the power of 4 and so forth. Okay, that's just a bit of an aside. The thing we're really going to do in this video is use Euler's formula. So let's take the original z, which was r times this trigonometric stuff, and collapse it down to this e to the I theta. That is, I'm going to get a polar form where my z is now written as r times e to the I theta. In some sense, you can just think of Euler's formula as just a shorthand for this presentation that we've talked about previously for complex numbers. I'll also add two different pieces of terminology. One is that we'll talk about the magnitude of our complex number, which we'll denote by vertical bars. And the magnitude of that complex number is just going to be the value of r that's out the front. Indeed, the e to the I theta part, or alternatively, the cos theta plus I sine theta part, that lives on a unit circle, and the radius of that unit circle is just 1. So that doesn't really contribute to the magnitude. So the magnitude is just, well, the coefficient r out the front. And then the other piece of terminology is what we'll call the argument of the complex number z, and that's just a different way of terming the theta value that we've seen before. Okay, so why do I like the polar form for complex numbers? Well, one reason is that it simplifies a lot of computations. For example, consider the following. I want to multiply two different complex numbers, both represented in polar form. So I've got a z1, which is an r1 e to the I theta 1, and then I also have a z2, which is an r2 e to the I theta 2. So now let me try multiplying the two of them together. The point here is that I can use rules about exponential functions. So for example, if you take the product of e to the something and e to the something else, then you get the sum up in the exponent. That is, this is the same thing as the coefficients out the front, the r1 and the r2 can just be multiplied together. And then in the exponent, it's e to the I theta 1 plus theta 2. Now, we could actually do this without this convenience of polar form. In fact, we did this in the previous video where we took two different complex numbers represented by coses and sines with two different angles. We multiplied them together. There was a lot of trigonometry, some trig identities came into play, and then it simplified to get the same idea that when you multiply by two different numbers with two different angles, the resulting complex number has the sum of those two angles. It's theta 1 plus theta 2. It's just that this exponential notation allows us to bury all of that sort of more complex trigonometric stuff. So nevertheless, we have that if you multiply two complex numbers, then the complex number you get out of it, the magnitude of it, is just R1 times R2. It's the product of the two magnitudes. And then the argument, or the angle, is just, well, the sum of the previous two arguments. So indeed, the multiplication of these two complex numbers has this length, which is R1 times R2, so just the product of the two magnitudes of the individual complex numbers. And then the argument, or the angle of this new complex number that is the multiplication, is just, well, it's just the sum of the two previous angles. Okay, so let's just practice the conversion where we start with a complex number and we put it into polar form. So one example is root 3 plus I. How is it represented in the complex plane? So one example is root 3 plus I. How is it represented in polar form? So if I visually look at what's going on here, I plugged in the point root 3 plus I on the complex plane. So the horizontal represents real numbers and the vertical axis represents going up to imaginary numbers. So I can put that point root 3 plus I on. I draw a sort of template circle that's got that radius. And the real question is, well, what is the radius? So going from the origin 0, 0 out to my point root 3 plus I. And then what is the angle with the positive x-axis? If I know the r, if I know the theta, then I'll have my polar representation. Okay, so let me focus just on that triangle. The base of that triangle, because it's got a real component of root 3, is just root 3. The height of that triangle, because it's got an imaginary component of I times 1, is height 1. And then just by Pythagoras, what is the hypotenuse? It's the square root of 1 squared plus root 3 squared. In other words, 2. So in this example, the radius is 2. Okay, what about the argument? What about the theta value? Well, theta from this triangle is arctangent of 1 over root 3. And indeed, this triangle is one of those special triangles. It's the 1, 2, root 3 triangle. And I know that that special triangle has angle theta equal to pi over 6. And so then the polar form of this is going to be z is 2 e to the I pi over 6. That's my polar form representation of the complex number, which is represented originally as root 3 plus I. Let's see one more example and really try to illustrate it geometrically as to just how valuable the polar form can be. In this final example, I want to consider the cubed root of minus 1. The square root of minus 1 was defined to be I, but what about the cube root of minus 1? Another way to think about this is that this is the solution to the equation x cubed equal to minus 1. This is a third degree polynomial, and as we saw in the first video on our series in complex numbers, that the third degree polynomial, by the fundamental theorem of algebra, ought to have 3 complex roots. Well, if you've seen this before, you might have said, well, minus 1 is an answer because minus 1 cubed gives you minus 1. So you might say the answer to this is minus 1. However, if you recall the first video that we looked at the algebraic side of complex numbers, the fundamental theorem of calculus said that if you had a degree 3 polynomial, it would have 3 roots. Indeed, this is just the solution to the polynomial x cubed equal to minus 1. So we have one answer to it, minus 1. But we should be searching for 2 other complex answers, and how can we get those? So I think what I'm going to do is start with minus 1 and try to write the minus 1 in polar form, hoping that polar is going to make things a little bit easier. So I can take this minus 1, I haven't taken the cube root of it yet, and I'll observe that minus 1 is, well, cosine of pi would give you minus 1 and sine of pi would give you 0, so this is just e to the I pi. Now, the reason I like writing it in polar form is now I can take to the power of 1/3, which is the same thing as cube roots. I can take that a little bit easier. So I can take the minus 1 to the 1/3. And then I know how to take e to the I pi to the 1/3. It makes it e to the I pi divided by 3. Okay, that's one of the 3 answers. We'd already guessed minus 1 as being the other. Why does that not appear here? And how do we get the third? Now, the issue is that this polar form actually has some periodicity to it. If I have some angle theta, and then I take that theta and I add 2 pi, I go the entire way around the circle, I end up exactly where I began. So the point is that I can actually replace I pi with adding any number of 2 pi. So I'll write this as 2n pi, where n is some integer. So the point is, the polar form of it is all the different ways I can write something within 0 to 2 pi, because outside of 0 to 2 pi, it's just repeating those values that were within 0 to 2 pi by the periodicity of cosine and sine, and thus likewise e to the I times theta. Okay, so let me do the same thing when I take the division by 3. It's going to be pi plus 2n pi divided by 3. So the real question is, when is this argument, this pi plus 2n pi divided by 3, when is that in 0 to 2 pi, which is the canonical way to represent it, somewhere in the first 2 pi circle? That's how I decide what my angle theta is going to be. Okay, well, let's just try listing them for various values of n. I'm going to have, if n is equal to 0, just pi over 3. If n is equal to 1, then it's pi plus 2 pi over 3. If n is 2, then it's pi plus 4 pi over 3. If n is 3, then I would end up with a number that was larger than 2 pi, because I would end up with 7 pi divided by 3, which is larger than 2 pi. So, in fact, there's only 3 values of n, 0, 1, and 2, such that the resulting theta lies between 0 and 2 pi. So all the other values of n are just going to repeat these numbers over and over and over again. Okay, so this is really good. 3 different angles, which makes sense because we thought there should be 3 solutions by the fundamental theorem of algebra. And then I just need to write them a little bit of a nicer way. So I think what I'm going to do is say the polar form is thus e to the I pi over 3. That's the first of them. The second one, pi plus 2 pi is 3 pi. 3 pi divided by 3 is just pi, so e to the I pi. And I'll note that e to the I pi, as we saw above, was just minus 1. So the second one is exactly what we've seen previously. And then the final one is e to the 5 pi divided by 3. All 3 of those are going to solve the equation x cubed equals minus 1. 3 roots to a degree 3 polynomial. Okay, so algebraically, we've seen why this is really nice. But let's go and try to take a look at what this means geometrically. So if I put up the plot here of the unit circle, and I've put on the yellow dot here to denote the number minus 1. That's where it occurs, one step to the left on the horizontal axis. In the complex plane, that's number minus 1. So I'm looking for the 3 values x, where when you cube them, you get to minus 1. Let's actually do the middle one first. Recall that e to the I pi we had said was just equal to minus 1. Okay, so the way I visualize this is I'm going to take e to the I pi times e to the I pi times e to the I pi. So the first one of them, I can plug this in here. It just looks like, well, an angle of theta, a length of 1, and e to the I pi gives you the value of minus 1. If I already have that and I multiply by e to the I pi again, so minus 1 times minus 1 is plus 1, it would then rotate another pi around the circle and it would be back over to 1 as we suggested. And then if I multiply the third time, so minus 1 times minus 1 a third time, it would take me back over to minus 1, which would be another rotation by pi. The point is, I really think of this middle one as rotate by pi, rotate by pi, rotate by pi again. That's going to take me up to minus 1. Okay, now let's do the first, the e to the I pi over 3. Well, where is e to the I pi over 3? So they all have length 1, so they're all on this unit circle. But pi over 3 has an angle, well, about there. Okay, so what I'm trying to imagine is cubing this number. So I take this number and multiply it 3 times. And what that means is that each time when you multiply, that you're rotating by an angle pi over 3. So I start with 1 pi over 3, I then rotate a second time and it moves over another pi over 3, and then it moves over the third time, another pi over 3, and takes me to minus 1. And so thinking of these numbers as rotations, this is a way that I could rotate the same value 3 times and end up at minus 1. Okay, what about the third one, this e to the 5 pi over 3? Well, 5 pi over 3 is over here somewhere. So I'm going to be cubing it, so I do it once, it takes me over there. I do it a second time, it rotates a further 5 pi over 3 around, and takes me now down to here, and then I rotate a further 5 pi over 3 around again, and this takes me finally to minus 1. So what we have here is a very pleasing geometric way to think about these 3 numbers that we algebraically solved using polar form. If you want to try and challenge yourself with another example, why don't you try the cube root of I next and see if you can find algebraically the solution to the cube root of I and geometrically predict where they should lie to cube out to getting to the value of I instead. All right, so that is polar form for complex numbers.